Hello, this is Greg Allison with Galactic Gregs, coming to you from an undisclosed location somewhere in the Milky Way galaxy. This presentation is going to be about orbital fuel depots. It's going to be by Tom Perrin. The title, Fill Her Up, a functional analysis of a cryogenic propellant depot at the Earth Moon L1. If you've not subscribed to my channel, please subscribe and bang the update notification bell to get notification of more videos to come. And check out my other videos. I haven't got everything listed on top right now, so click the video section under my YouTube page. And be sure to click the links below to support my channel.
Hello, I am Greg Allison, president of the Huntsville, Alabama L5 Society. We are the local chapter of the National Space Society. We formed here in 1983. We have engaged in a lot of activities over the years. We've had 2 International Space Development Conferences. We've done many projects on the side. The one that's most noteworthy is we developed hybrid rockets and launched altitude balloons and got in the Guinness Book, and we spun off companies and other projects and things spun off from that, and a couple of our members, including our vice president sitting in the back of the table, works for one of those today. So this organization is dedicated with a long-range goal to grand space development to the point of humans actually living and settling in space. All right, tonight, the topic tonight is orbital refueling, orbital fuel depots. And this is something I've had a great interest in for a long time. And I think it's a type of capability that can buy us a lot toward the dreams that we all aspire for grand development of space. And our speaker, Mr. Perrin, Tom Perrin, is a graduate of the United States Military Academy at West Point, where he got a BS in Mechanical Engineering. He holds an MS in Systems Engineering from the University of Alabama in Huntsville, UAH, and an MS in Space Studies from the University of North Dakota. He has 30 years of experience working in military and civil space, and currently he works for Aerodyne Industries as a subcontractor to Jacobs Engineering. You can tell I go back when I want to call him Spheredrip still. And he's working as a senior ground ops systems engineer supporting the development of the Space Launch System. So I anxiously wait to see what he's going to say here. Ladies and gentlemen, Mr. Tom Perrin.
I worked on Constellation back when Constellation was a program, and in 2009 and in 2010 when they verified or confirmed the presence of water deposits at the poles, I thought, man, we are good to go. You know, there was some talk back then about, you know, will Constellation continue as a program or not, and I thought, man, we got to go now. We're in good shape, you know, because they've discovered water, and that'll be all the motivation we need to build this rocket system. I was wrong. So Constellation was canceled, and you all know that story. But I was really interested in the notion of fuel depots, because my thought was, if there really is water there at the poles in any significant quantity, then that's a real game changer. And it seems like to me it wouldn't be real hard to envision sort of a lunar economy built around water and hydrogen and oxygen. So I've been interested in fuel depots for a while. The work I did for University of North Dakota, my thesis work was looking at architectures for propellant depots, and that's kind of, this just sort of continues from that. One of the things I noticed over the last year or two, looking at different things in literature, that you can look at different concepts for depots. There are lots of papers out there about depots, but I didn't see anything that really went deeper, a whole lot deeper about what it would take to put together a depot. And so I wanted to look at the notion of a functional analysis for a depot, and that's what this is all about. This is the methodology I used. I reviewed a number of relevant past studies, and from those kind of synthesized the concept of operations. And from that, extracted what I thought the functional requirements for a depot had to be, and then did a decomposition and developed functional flow block diagrams and intuit diagrams and tried to draw some results and conclusions. This is a little bit about the concept of operations. Located Earth Moon L1. I see it as being operated from a ground station on Earth, supplied by resources from the moon. Need to be modular and expandable, as assumed the demand would grow over time. And I had this idea of mounting propellant tanks radially around a shaft. I'll get back to that in a minute, and have that shaft driven by what I call a rotisserie motor, like my father-in-law used to have this rotisserie thing on his grill, and he'd put his bird on there, and it would go over the fire for however many hours. Each propellant tank would have a lot of its own equipment: a cryocooler, instrumentation, mass gauging, mixing device, venting, and a propellant transfer point.
So these be robotic LRUs, each tank?
Yes.
I came up with the concept and drew it up based on that in the 80s.
Okay. This slide kind of expands on that a little bit. There's a fellow named Dallas Beamhoff who used to work for Boeing years ago, and had a briefing in 2007, this Boeing concept at the upper left. I'm sorry. And I think what he was trying to show in his briefing was just a method of construction, of taking something up, and then repurposing it, once you got on orbit. But that picture kind of stuck in my mind, and I thought, well, gee, if I could rotate that thing, then that would solve some problems, because we haven't really transferred cryogenic fluid in space in any quantity that I know of. So if you could rotate the thing, then your centrifugal force would drive the fluid, your propellant, to the outside of the tank. Any kind of gaseous propellant we'd have would be ullage, which could be vented. And so it seemed like to me like it would attempt to address some of the problems that we have in handling cryogenics.
So the rotational concept is yours to do this?
Yes. So now start looking at an initial functional breakdown. What in terms of functions, what it would be. What I show here in the What I show here in the middle, structures and mechanisms, attitude control, power terminal. These are things that any spacecraft are going to have. Those are systems all spacecraft are going to have. So then I started saying, okay, what functions would I have to have for propellant operations? And so you see I've got propellant operations. It comes down here. I've defined 4 basic areas, what I call propellant maintenance, propellant receiving, propellant dispensing, and then what I've called contingency recovery. Breaking those down further, propellant maintenance, obviously cryogenic liquid oxygen, liquid hydrogen, very, very cold. And so your problem is how to keep them cold and keep them fluid. So there's things that are going on all the time, and that things that the depot would have to perform. So you'd have active cooling. It's pretty common knowledge that passive insulation like MLI is not enough to prevent boil-off, so we'd have to have active cooling, cryocoolers. We'd probably have to have some way to vent the tanks. We'd have to be able to mix the cryogens inside the tanks to keep them uniformly, the temperature uniform throughout the fluid. You need to have some way of measuring the temperature and pressure all times of the tank. You don't want the tank to rupture for increased pressure. And I've got rotating the propellant tank, as I described earlier. And then lastly, mass gauging. Rotating the tank would allow you to perform settled mass gauging, which would be a lot easier than trying to determine how much mass of propellant you had in a tank just in weightlessness. So this is a functional flow block diagram. The norm for these kind of diagrams is you have a starting point. I did it again. You have a starting point and an end point. So here I'm saying that in the propellant maintenance of the depot is going to periodically be reporting its status to the Earth. And how much propellant's on hand, what's the condition of that propellant, pressures in the tanks, all that sort of thing. And that'll go on pretty much continuously. The propellant receiving and dispensing are almost identical, so I combined the diagrams for those functions. So the starting point in this case is the propellant maintenance. That's an activity that's going on almost all the time. So there'd have to be some sort of communication. Hey, I got a customer coming, or I got a tanker coming. The two spacecraft get close together. That'd be a grounding between the two spacecraft, make sure there's not any electrical issues. Finally, the docking. And then once you have a physical docking, then you'd end up with a fluid mating. Anytime you transfer a propellant, you have to have a chill down of your tubes or pipes that you're going to transfer the propellant through. And then finally pumping the fluid. Then there's probably going to be some sort of a mass gauging operation. You know, you fill up your tank, you go fill up your car, and you say, well, did I fill it all the way up, or did I not? How much did I pump? How much, in this case, how much is left from the supplier vehicle, or how much did I pump into my customer vehicle? And then you start undoing things via fluid demate, and the spacecraft undock, and the spacecraft would go their separate ways, and you'd be back to a propellant maintenance condition.
Did you decompose any of that, like your mass gauging function?
I did not. This was the level I took it to.
Okay.
Obviously, that would be, you know, a next step. Contingency recovery. It says number one. There's the diagram's too big for the slide. Again, I'm starting in propellant maintenance, and I'm looking at possible failures that we would have on the depot. And say, okay, you might have a cryocooler failure, or you might have an instrumentation failure, or my mixing device inside the tank might fail, or there might be a failure in a leak detection system, or mass gauging, or the motor, or venting and whatnot. And so any one of these things could happen and would have to be dealt with. And then once it was dealt with and you got back to a steady state, if you will, then you go back to propellant maintenance. Two other failures that I considered would not have as their starting point the propellant maintenance, but they would have as their starting point the receiving or the dispensing operations. And those had to do with, you know, one, the transfer pump failure. Pump fails and I can't pump my fluid, or a vapor lock. A vapor lock would be if you had a transfer pipe that was not properly chilled, and you go to pump cryogenic fluid through it, and it vaporizes immediately, and you have the pressure and doesn't permit you to pump any more fluid through the pipe. So that's a double problem. So then those would be problems that you would see during receiving or dispensing operations. The next slide is more of a contingency recovery detail. This kind of gets to what you were asking about a little bit. If you have some nominal operation and you have a failure, whatever that failure is, the failure occurs, there may be some time lag before you actually realize that a failure has occurred. So failure occur and then failure detection, and then what are you going to do? Well, maybe there's some sort of a workaround, or maybe you can go repair whatever the problem was and continue operation that way. Or maybe you have to replace something, replace the cryo-cooler, replace, you know, some other piece of equipment and get back to your nominal operations. So this is just a way of taking it down one more level in terms of contingency recovery. Next thing I wanted to look at was interfaces, and that's what the N2 diagrams are about. If you're not familiar with them, and I wasn't until I did this, an N2 diagram is a way of looking at functions or systems and trying to figure out what the interfaces between those systems or functions might be. And so what you do is you identify all your functions, which I have done here, and you array those on the diagonal of your matrix. And then everywhere there's an interface between one or two of these functions, then you end up having an intersection. So in this case, I've got structures and mechanisms, and I can see that I've got a thermal interface, a mechanical interface for thermal insulation. I've got a mechanical interface for attitude control. I've got a mechanical interface for propulsion. I also have a mechanical interface for propellant maintenance and for propellant receiving and dispensing and contingency recovery. All of those will be involved mechanical interfaces to structures and mechanisms. The blue that I've circled, the command and data handling function for the depot, I see that as being electrical connection to all the other functions. And then here by C, I'm saying that CDH is commanding. It's commanding, you know, the attitude control system to give it some sort of a report. What's your status? Similar to, you know, propellant maintenance. What's your status? And then I see the return as being electrical connection, but being a reporting function back to the C and DH. At the top, the way the convention goes for N2 diagrams, you have inputs into the system at the top and outputs from the system on the side. So again, this was propellant depot functions. I did another diagram where I looked at propellant systems and subsystems. So you can see I've got you know, mating here. I've got the CDH up in the corner, the rotisserie motor, the instrumentation, gauging, cryocooler, mixing device, propellant tank, and on. It became very clear to me that the propellant tank is sort of the center of the action. You've got interfaces up and down the line with the propellant tank. They're either surrounding the propellant tank with interface with the insulation, or I'm doing propellant mixing inside the tank. I'm pumping something from the tank or into the tank, out of the tank, on and on. There's all these different mechanical connections to the propellant tank. Also, as we saw before, again, you've got the command and data handling system, and it again does this commanding, has electrical interface and does this commanding of all the other systems, and those systems report back through the CDH, you know, their status. Again, across the top, receiving commanding, interface with supply vehicle, receiving propellants, sending reports, interface with a customer vehicle if you're supplying or dispensing propellant to another vehicle, and then supplying propellant. It seems so easy. I mean, it seems kind of simple. It takes me, what, 5 minutes stumbling through this, but I spent weeks, you know, wrestling with this, you know, how do you do this? So some results. It seemed like to me, after I spent all the time that I did, that the four functions that I tried to identify, the propellant maintenance and the receiving and the dispensing and the contingency recovery, seemed to me to completely describe the spectrum of the operations. I couldn't think of any other thing that might go on that wasn't covered under those four areas. Second thing was pretty obvious, was that C&DH is a critical system for the depot. Third, the diagrams highlight the many fluid, mechanical, and interfaces with the propellant tanks. And I thought, gee, you got a propellant tank, and I got mechanical things going into it, I got electrical things going into it, and that's kind of scary, you know. But it's in a vacuum, you know, maybe it's not the hazard I think it is, but it's kind of scary. So I thought, well, maybe special precautions be required in the design and operation to make sure you have safe operations. The other thing that jumped out over and over again as I looked at the various failure modes, almost any anomaly, whether it's a mixing failure or a cryocooler failure, or maybe you got penetrations through your insulation or whatever, almost any kind of anomaly is going to result in a temperature and pressure spike to the tank, which means you know, you probably end up having to vent the tank to make sure you don't have pressure too high. So it's pretty clear that the status of the tanks has to be, you know, continuously monitored all the time, just to make sure you know what's going on and stay on top of it. Conclusions. I felt like the functional decomposition and the diagrams and all that were pretty good tools. I felt like I gained some understanding of what I was about. Secondly, redundant systems should be considered for critical functions where there's no immediate workaround for a given failure. Third, as I mentioned a minute ago, the response for many contingencies is to vent the propellant tanks to prevent tank rupture. One thing somebody mentioned to me is, well, how fast is the vented gas, vented propellant going to dissipate away from the depot? Don't know. Don't know anybody knows, you know. And so that's a question. Would it be a problem or not? So I saw that as a topic for future study. And then another thing that somebody pointed out to me is that you have commanding from the Earth. Well, that takes about a second. You have a second communication latency back and forth. There might be a condition that occurs where that second could be really critical. You know, so maybe you consider, although it's envisioned to be operated remotely, you know, maybe some sort of autonomous operation might be required to respond to some emergency condition. And there you have it. What questions do you have or comments, please?
If you have to vent gas or liquid, probably a gas, that'll act like a jet. It'll give a force to it, which can affect what's happening.
Good thought.
So you have to have RCS to compensate for some of that perhaps, and for attitude control. So was attitude control part of your decomposition?
I thought I not as far as decomposition, I thought I had it
As a function?
as one of the,
In two diagram functions?
I thought I had it on here, but I forgot and left it off.
It's one more slide.
Hmm?
One slide forward, or two slides forward. There you go. Or no, one more slide. I saw something in there about attitude control. Next one? Yeah.
Oh, yeah, it's in there as far as
There we
the,
go. It's part of the regular spacecraft, yeah,
Right.
functionality, of course.
but he's right. And I also had one person mention to me that maybe you could use the venting as a way of doing attitude control. You know, vent into an ACS thing. And I thought about that, and it just seemed too hairy to try and attack it, you know, head on. So I thought, well, I'll put that away for a while. But that's a really good point. Another point is that, you know, the diagram sort of hints that the tanks will be the same size. Well, they can be. If you had 3 hydrogen tanks for every oxygen tank, you could have them about the same size, but the mass of those tanks will be quite a bit different. So if you're going to have these things rotating around the shaft, then you're going to have to say, well, how do I do that to make sure things are balanced? And you know, so there's all kinds of issues. Another issue is if I'm going to spin this thing and I'm going to drain it, I'm going to service the customer and I'm going to drain the tank from the outside edge of the tank. What does your piping look like? What kind of piping and manifolding? That could be really hairy. And then, of course, all that stuff would have to be cooled before you can push anything through it, you know. So there are lots and lots of issues. You know, the basic idea seems okay, but the devil will definitely be in the details, how you can make it work. Yes, sir.
So one of the first things I think about is safety in terms of what if one of your tanks explodes under whatever conditions, whether it's a meteor impact or whatever it is, then what does that do to your other tanks? How are you going to prevent that effect from
Failure propagation.
Propagating?
I didn't even consider that.
Propagation is what we call it.
Also, you unbalance your centrifuge as well.
Oh, yeah, yeah.
So you'd have to halt rotation first.
You'd have to assume that if anything can go wrong, it will.
Oh, yeah.
And then
Including the docking. The docking could go wrong, you know.
as a control, you could actually have some kind of shielding or something to deflect.
You'd have several controls,
whatever,
and
yeah.
stuff like that. Then what do you do if it happens, you know,
Yeah.
so there's the event management. Controls are like, you have hazard controls. They're intended to prevent the event from happening, but then what do you do after the event happens?
Yes, sir.
So question, related to that, I might miss this. Do you have a method to keep, since you're talking about rotating this tanks in a but would be a fairly high-speed situation. Do you have a way to equalize the propellant between the tanks? Or have you considered a way to equalize the propellant between the tanks?
I had not considered that. It's not a bad idea.
Sounds,
It'll start to oscillate otherwise.
yeah.
Yeah. Yes, sir.
Well, okay, what about this? You could vent along the axis and have like a pair of vents there so that,
I'm sorry?
well, okay, what about venting along the axis? And just have a pair of vents so that they'll both equal out, they'll both produce
You're venting always.
equal and opposing
Yeah.
thrust to each other.
That's for nominal venting, but wouldn't cover financially.
Also, also for keeping everything balanced, you could vary the distance the tanks are from the main axis. Just have them like on a boom or something that you can move
Yeah.
up and down to
That's a good
maintain
thought.
balance.
Yeah, that's a good thought.
Boy, it's getting complex in a hurry, isn't it?
Yeah.
You just thought it was complex before.
So you consider maybe using water as the main storage medium and converting it, electrolyzing it and liquefying it before use in a just-in-time type system? Because water's a whole lot easier to store and deal with than.
I did not, and I'll tell you why not. There's a fellow at KSC, give me a minute, I'll think of his name.
And you get it as water initially. Maybe.
You were gonna make it just
Can't
in
think of
time
his
to get
name,
an
but-
awful lot of power.
But
Well, yeah,
that was it, and I talked to him about it, because he wrote a great paper that I've resourced several times over, and I met him at a conference, and I said, so how much power is it take to, and then the answer was a lot, and a long time to do, the hydrolysis and the liquefaction and all that, and so it didn't seem to me to be a very practical thing.
Just a good nuclear power plant on handling.
Well, hey,
I think the nuclear power plant will be on the surface of the moon. That's what I think. And they'll do all the work down there.
Well, 225 kW power modules, right? So if you had resistant jets, though, you can actually get 4,000 seconds of ISP with resistant jet just with water. But of course, you don't have your thrust buffer in space. That's kind of interesting.
You could beam the power from the moon for the system.
You still got to have a big rectangle there.
Yes, sir.
What about arranging instead of arranging the tanks radially, what about axially? And have the tanks like going along the length along the axis, and just rotating a pair of tanks. Instead of that flower arrangement, more like have like two tanks like side by side and they're rotating. We're probably.
Then the force would send the propellant where?
I mean, it would still there would still be centrifugal force, but it would be
To the tank
it would be
wall.
like the radius of the tank instead of lengthwise.
Yeah.
You could change the shape of the tank too.
Yeah, I'd have to think about that. I mean, obviously you could do it. I'm not sure.
For instance, if you took a
You don't get as much
spherical tank,
acceleration.
the area that your liquid goes into gets compressed, is less than the full width of a tank.
Right.
So that would work better also for getting it out, for pumping it out. Pumps itself.
Yeah. That's one thing I discovered from having attended several conferences. Now, at first time I attended the conference, I thought the paper that I presented had to be absolute truth that nobody could argue with, right? And you never get there. And then later on I realized that really what the purpose of the papers are is to spur discussion, just like what we're doing here. So certainly seemed to have done that. JJ?
Okay, so another question. What was your plan for docking and fueling spacecraft to the propellant? Are you planning to try and put them on the edge of the thing, or are you trying to hook it up?
Where do you dock it? Center axis or?
I didn't spend any time trying to develop it, but my thought would we'd have to be on the center axis somehow or other.
This is more of a functional decomposition than
Right.
design. Your whole approach here was what functions do you have to address?
Right.
And you did a great job of that.
So,
So design, you know, is something you kick around with a lot of trade studies after.
Oh, yeah.
So great.
Yeah,
Functional
it'd be-
decomposition is excellent here.
you know, but if you got this thing that's spinning and you have to try and dock to it, you have to dock to one end or the other, and then I can see all kinds of issues with seals and
Well, remember with
manifolds and on and
Remember
on.
2001 Space Odyssey, at the very beginning, when they're docking to the space station, and they have to start rotating the spacecraft to match the rotation of the station,
Yeah.
and before they can
Also
make.
relying on the space station, it was pretty large, and
They're not moving that fast.
yeah.
I mean, part of it's how fast the actual tanks are rotating, so.
You could actually do all your spinning inside the tank.
Yeah.
And they were coming in
And
actually.
have it'd be like a gyro to some extent, each one.
Yeah,
All kinds of ways.
all kinds of things, but Jake.
Trade study space.
Yeah.
Does anyone recognize those tanks on the Boeing concept up there?
Yeah, it was like Delta 4 upper stages.
Yeah, they do. Hey, look like ICPS on the SLS.
Which is a Delta 4 upper stage.
Right, exactly. Sure do. That's Dallas Mine Hall for you, right? That's right, I did come from.
Well, thanks for letting me come.
Great, thank you.
When they first asked me about this, they said, we have to get advertising out, but advertising for me? It's like,
Any other questions? Anybody have any other questions for the speaker?
So are you going to do a sequel to this, or another study?
I
More!
don't know.
Hey,
I did have a question. I see a lot of open questions that you could continue this and get a PhD off, but.
2 or 3.
See that lady in the pink right there? I think she'd have something to say about that.
it sounded like cuss words, didn't it? You ought to know.
Yeah.
Actually, what I'm interested in looking into right now is if you buy off on this idea of the lunar economy based on water, then rocket engines, liquid hydrogen and liquid oxygen are going to be the name of the game. I had a professor at North Dakota who, by the way, drove a Volkswagen Beetle, probably a 30-year-old car. And he pointed out to us more than once that there would be a need for a rocket engine that was like his old Volkswagen.
Reliable.
Dead simple, dead reliable, maybe exchange, specific impulse and some stuff like that.
Manufactured by
Lower
Volkswagen.
trade, lower performance for high reliability.
Amen.
And so just this last week, I started pulling out some textbooks and trying to educate myself on rocket engines, and that's something I'm interested in looking into.
Hey, with Starship and everything going on, now might be the time to start developing, get your patent, and you might be the next millionaire.
It's interesting because Bezos has specifically said that he wants to refuel from lunar-derived hydrogen,
Right,
and
right.
they're working on a small hydrogen oxygen.
He's got that VE7
Yep.
engine.
Yep.
He had a display at the Congress, and they didn't have the engine there, but they had literature about it, and then I just don't know how simple you can get.
Yeah.
Yes, sir.
What you were talking about earlier is something I thought about because I've seen like how they had to work on like the shuttle and some of the components of the shuttle engines in a clean room, right? And they had to resurface and everything. Now, the rocket that you're talking about that's simple and robust would be a pressure fed rocket, which basically uses a blowout tank to push the fuel into the combustion chamber. It just uses pressurized air, like helium or something.
Mm-hmm.
Yeah, where are you gonna get the helium?
Well, not from the moon, not helium, you use something else.
Not from the moon, but it's compared to carrying around
Hydrogen.
fuel, that's not much of a weight constraint.
Well, I'd say that there's a.
It doesn't have to be helium, you could be something, it's another gas.
The other thing I find interesting right now is there's two underpinning architectures right now that are actually out there for the public to consume for getting to the moon and back in a sustainable way. One is the Bezos and other methods of utilizing the moon as the source of the fuel. But then there's what Elon Musk wants to do with Starship, where he wants to do all the orbital refueling in low Earth orbit instead, with methane instead of liquid hydrogen. And
Well, he's on the spacecraft to spacecraft too.
Right,
No depot.
right.
But that gives you, that locks you in a specific architecture.
That is a very, see, that's where I'm
So
going. is-
he's a multi-user architecture, actually, is what he's
But
saying.
it's also an architecture that makes more sense for Mars than it does for
Yeah.
the moon. But what you're gonna have, and this is discussions that we've been having in the hallways at work quite a bit, is sure, you're gonna have a hydrogen economy, but the coin of the realm of the moon is actually gonna be carbon and nitrogen compounds, because those are gonna be the ones that are gonna be harder to find, that you're gonna need to live off of. So-
Asteroids, lunar
Yeah.
poles.
So basically, you're going to find these niches in different economies in space that are going to be little islands of scarcity. And someone's going to have something that someone doesn't have, and it'll be a new way of trading.
Anything that's rare.
The thing I did for North Dakota a few years ago, I looked at depots in low Earth orbit, and the thermal environment's just all wrong. You want to be up higher where it's colder.
Right. You get a lot of reflection from
So you don't want to be close to Earth, okay.
No, not
Yeah,
at
I
all.
can see that for cryogenics, definitely.
And then,
That's why you chose the L1.
right, and then again, the study that I did, I looked at all the delta V's and whatnot, and the least amount of delta V for customers or suppliers or anything was to have it at L1. So.
All right, any other questions for the speaker? All right.
Well, thank you.
Tom, appreciate it. Very good talk. And thank you for watching.